The first theorem was a quenched. Now I make it more clear. I said it was halfway between quenched, and now as we are so in a more reduced audience, I tell you exactly what it is. Good? Because I said it's halfway between. So the theorem 1, same conditions and so on. What I state is the following: let f be a function from Rd to R, which is bounded and continuous, then it is true that expected value, quenched expectation of f xt by square root of t minus the normal, so minus, let me say, integral, okay, minus expectation with respect, let me put here normal, with sigma of f psi. Is it clear what I mean there? I didn't want to write the integral. Take absolute value of these two, of this difference, and then integrate on omega with respect to d pi, this goes to 0. Right? The weakest way would be without the absolute values. So that this guy integrating converges to this guy. So this is stronger, but it's not quite the theorem 2, the quenched says the following, that for pi almost, and the same, so bf like that, pi almost all omega in omegas, it is true that expected value of omega f xt by square root of t converges to expected value with respect to the normal, same sigma deterministic of f psi. So clearly this one is stronger. This one is stronger as long as sigma is finite. This is stronger than the weakest, which I didn't even say. So this is the theorem in the paper with Gadi, and this is the theorem in the latest paper. Now, let's see how we prove it. How I prove that. In order to prove, now we have to go to dirt our hands and do some mathematics. So as I told you, we are in the space omega. Omega, that's the station, that's the set, the environment, right? There are the translations and so on. And what I told you at the very beginning as a remark, that this pi is stationary for eta s, which is tau xs omega, which is a Markov process. Right? Now, if we are in a stationary case, then better we go to the L2 space of this and think about the infinitesimal general, semigroup infinitesimal general, so that I will define some operators on this Hilbert space. Let me take orthogonal to the constants. Just not to worry about that one-dimensional subspace, right? Orthogonal to the constants. So that's what I will call H. H is the Hilbert space of L2 orthogonal to the constants, right? And this is a Markov process which is stationary there, so it has a semigroup. It has a semigroup, so PT B, BTF omega B expected value starting from omega of F eta t, right? And PT, I just write formally PT is e to the TL. That means what I mean, that I will denote by L the infinitesimal generator of this semigroup, and this is a very concrete operator which I will write down. I need some time to define some operators in this space, and And that's okay. Some operators. Right. I will need something like gradient in this space. I will denote nabla E. Remind E was a unit vector. Nabla E, this is just notation, nothing surprising here, is F tau E omega minus F omega. Yeah? And of course you can see easily what is this is. Okay, what is the adjoint? Okay, you easily see that nabla E adjoint is probably, let me see, probably nabla minus E. I'm not sure if it's not minus nabla minus. And nabla minus. I think that is the case. Anyway, everybody can write down what the adjoint of this is. Adjoint with respect to this measure. So, and so on. I need the Laplacian on this space. The Laplacian of this space is Laplacian F omega is sum over E of F tau E omega minus F omega. I might put here on 1/2 or something. I don't care about these constants because anyway I will make mistakes with the constants, right? And I will need later something I call the Rényi operators, and this is a strong group in functional analysis, so it's no surprise. So I will denote by gamma E the Rényi operators. This will be delta the minus 1/2 nabla E. By the way, so this is self-adjoint. So by the spectral theorem, it makes sense to speak about this, and actually it's easy to write down explicit representation of this operator. So this is not logical. And what is very important that this is unbounded. This is an unbounded operator, but altogether the gamma is bounded. Altogether gamma is bounded because you have a gradient times Laplacian to the minus 1 is bounded. Write down the spectral representation and you will see that this is bounded. Right. I will still need some other operators, namely I will need an operator ME, which will, by the way, all operators which are expressed in terms of translations have joint spectral representation, so we understand everything.
So Laplacian here is a bounded operator.
Laplacian is a bounded operator because we are on lattice. Yeah? But this is not a lattice Laplacian, so it's a Laplacian acting like this. These are very related objects, right? It's a bound. All operators you see now, all operators are bounded. This will be a multiplication operator. Multiplication operator M sub E of F at omega is defined as multiplied by V sub E omega F omega. So it's multiplication by this, by the flow on that edge, right? And it's easy to see that the infinitesimal, I write down the infinitesimal generator, but this will be a very easy exercise for an undergraduate student. What is the infinitesimal generator? Let the Markov process evolve epsilon time, take P at epsilon of F minus F, divide by epsilon, and see what the limit is. And you just, on your fingers, you can compute it in this case because it's a simple case. So this will be Laplacian, might be a constant here. I don't care about constants. Maybe it's for 1/2. I don't care. Right? Plus sum over E in E, M E gradient. And I leave it for you to check. So why? Because you take, what is the infinitesimal generator? On each direction E, you jump with rate P sub E. But P sub E is 1 plus V sub E. And from the ones, as you sum over all E's, you get the Laplacian. And from the other, you get from the V's, you get this one. Right? Now what is a fact is that the Laplacian is self-adjoint. By the way, it's negative semi-definite. Right? And this part will be the anti-self-adjoint part, the skew self-adjoint part of my operator. So the divergence-free condition, remember, that's equivalent, and this is again an easy exercise, the commutation relation of these operators, which I'm writing down right now, which means that sum over E of ME nabla E plus sum over E of nabla minus E ME equals 0. And I leave it again for you. It's an easy exercise, easy elementary thing to check that the condition I started with, the double stochasticity, is equivalent to this commutation relation between the operators. With the sum, not one by one. So it's not the case that that equals minus that, but the sum is true for the sums. And this is again the case. From where it also follows that this is minus S plus A, just notation by minus S I mean the symmetric part, and I prefer this notation to keep S as a positive operator, and A is the skew symmetry, or skew self-adjoint. And all operators you see there are bounded. No problem. I tell you in advance, the problem, all these problems arise not by unboundedness of that. If that is unbounded, it's a nuisance, you have to be careful. But the true problems come from the fact that this is not inverted, that the inverse of this guy is unbounded. From that unboundedness comes the
Just, can you remind me please that VE, yesterday you defined, I think.
Yes.
VE.
Yes.
What's the form of VE?
I tell you, so VE omega is 1/2 PE omega minus B minus E tau E omega, and this is minus V minus E tau E omega. And from here, and the translation and all that elementary things. Okay. Now, recall X, the martingale decomposition. We had a martingale decomposition. We had xt as xt minus integral from 0 to t phi eta s ds plus integral from 0 to t phi eta s ds, which is just a tautology. Whatever phi is, this is true. But I choose the phi omega. This is in RD. This is an equation in RD. Phi omega is sum over E in nearest neighbor, E times PE, but that is the same as sum over E in E times VE. Omega, we simplified our problem such that the symmetric part is just constant, just not to carry more things which are not really relevant. So this is the phi I choose. This is the instantaneous drift, local drift of my random walker. So what I subtract is exactly the compensator. So this is the martingale. And as I told you yesterday, the difficulty is to understand this part. What does this mean? Now, there is a big theory. A big theory which, okay, everybody has heard about Kipnis-Faradan theorem or Kipnis-Faradan type of theorem. Let me call it Kipnis-Faradan theory because it's not just the Kipnis-Faradan theorem. And let me just, for sake of historic correctness, let me say that it didn't start with the paper of Kipnis-Faradan in 1986, which all of you have heard about. But earlier, I just discussed this this morning with Rajat, There was a paper back in the 70s by two Russians, Gordian and Lifshitz, Gordian and Lifshitz, who did something simpler than the Kipnis-Faradan, but the idea of martingale approximation was there. So it's fair to say that there was Gordian and Lifshitz, then came Kipnis and Faradan, and many more. Now, the theory is about exactly this. So let's make abstract, forget about the very concrete case. I have a Markov process on a stationary and ergodic Markov process on this space, with L, the infinitesimal generator, write the infinitesimal generator as symmetric plus anti-symmetric. So forget about the concrete content. Think abstractly about the Markov process. Markov process on a space, stationary, ergodic, generator, and so on. And the problem raised in these papers, which is very, very natural, is take a stationary and ergodic Markov process, take a function, an element of this space which is zero mean. Is it true that this integral, is there a central limit theorem for this integral? This is a classical problem, right? Very classical problem. So if the Markov process is finite state, is omega happens to be, so that's what we teach. If the Markov process is finite state, then there is a central limit theorem, and in some of our courses we teach this to students. It's not trivial. Even in that case, it is not trivial. So if you have a finite state Markov chain, and you want to prove central limit theorem for an integral of a function along the trajectory, the natural thing you do is the following. Take return time, name one of your states, call one of your states the origin, and break down to excursions. The excursions are independent, add up what happens in the excursion, but you will have some extra garbage, you will have some other difficulty coming that the number of excursions is random and it's not unrelated, it's not independent of what happens in the excursions. It's a bit subtle, but in this way you can prove the central limit theorem. There is need of very fine estimate, or more or less fine estimate, of the return times, which are exponentially tight, and other things. This can be extended, this proof can be extended to the numerable Markov chains if they are, how do we call it, strongly ergodic, or they have, how do you say that? If they have sufficiently tight return times, right? You can do that, but not beyond that. Not beyond that. And in particular, if your Markov chain is continuous state space, then this doesn't help you at all. Right? And this is a difficult problem. And the Kipnis-Faradan theory is about how to treat this type of problem. And it's starting, I don't have time to go into all details, but there are lots of theorems here. I will tell you one of my theorems, which I will use actually, that under conditions, various clever or important or conditions on the operator, which is minus s plus a, and phi, the function. You have two types of condition, one on the operator, sort of spectral condition on the operator, and another condition of phi. I will tell you both in my setup. It is the case, so this is a general structure of a Kipnis-Faradan type martingale approximation. It is the case that integral of 0 to t of phi eta s ds can be written as a martingale, let me put here, depending on phi, martingale with respect to the filtration of the Markov process, plus an error depending on t, because there is a decomposition, so it may be, in very lucky cases you don't have this, but those are boring, those are not interesting. So you have an error, you have to find a good approximation. So let me not go into details. Such that this is small order of square root in L2. Let me see, yes, L2. Because L2 is not L2 over omega, L2 of the all of the probabilities altogether. So the variance of this object is small order of t. Right? Is it more or less clear? I didn't tell you details because there is a very it's Hilbert space. It's factorial theory. Hilbert is functional analysis. What happens here? But I don't have time to tell you. Now I didn't tell you what the conditions are. So the original
PTRF paper. I just remind you. It reminds me. PTRF paper in 1982. Ravi Bhattacharya's paper.
Who has?
Ravi Bhattacharya's paper. Ravi Bhattacharya.
Bhattacharya, yes.
PTRF, 1982.
Yes.
If xt is Markov process, then f of xt L2, f is L2.
Yes.
Then integral of 0 to t. There's a central limit theorem done in there.
But under some conditions.
Exactly. Under that, f satisfies that L of h condition, something like L is an operator.
Oh, but
yeah.
Okay. Let me come to this
Yeah.
one. Let me come to this one. If I understand well what you are saying, but maybe I don't. So if I understand what Bhattacharya says, probably I will make some mistake. Is that more or less correct?
Yes.
Good. If I understand what you say, is the following. If phi is L of psi, if
Yeah.
phi is in the range of L,
In the range of, yeah.
if phi is in the range of L, then this holds.
So you are using the L's plus some errors here.
Yeah, there is some, in
Yeah.
this case there is some error, but it's easy to handle.
Yeah.
Now this is exactly Gordian-Lipschitz. This result is equal. I didn't know about this one, but this morning I spoke with, I told to Raja, this is exactly the same as Gordian-Lipschitz. Sometime in the 70s.
I can't recall. I can recall Bhattacharya's paper. I was thinking about the same thing. But I also recall Bhattacharya mentioning Gordon-Lipschitz in that
Maybe,
paper.
okay, then maybe.
So, but I can't recall what the difference is.
do it for discrete time Markov chain. So
Yeah, that's right. So you embed
Gordon-Lipschitz do it for discrete time Markov chain, but the idea is that, and then instead of L, you take P minus identity, which is the same thing, and that's exactly what Gordon-Lipschitz.
I think Bhattacharya also does the same thing. He defines stopping time and breaks it into.
Yeah, stopping time. Yeah, stopping time.
Anyway,
But no, this is for general state space.
This is for general state.
General state.
This is for absolute.
Condition
So if you
Yeah,
have
this
this one,
condition is
if you have this
fine.
one, just write it. You get it for free. You get the martingale and you get an L2 term, which is easy to handle. But I don't exactly know what is in Bhattacharya because this is the first time.
Reading that paper when I was a research scholar. So.
Sorry.
I remember reading this paper when I was a student.
Yeah, but I don't because I didn't know. But and he mentions Gordon-Lipschitz, so there must be some difference which I don't know. But essentially, this is Gordon-Lipschitz. This is what I said that it didn't start with Kipnis-Varadhan. It started with Gordon-Lipschitz and Bhattacharya. It's the same time, doesn't it? So these are a few years difference. They didn't know about each other, so it's no priority. But anyway, this is a nice result, but it's very rare that this happens. This will not happen. This will not happen.
Yeah.
What you have to do is do some approximation. So approximate phi with elements like this and control the error and so on. Now I tell you there are stops, there are milestones on this road. There is Kipnis-Varadhan in 86. I have myself a paper in 86. For this is so reversible. U equals L star, A equals 0. I have myself a paper in 86 for non-self-adjoint, slightly different than for random walking element. I don't tell you details because I don't have time. Now there is a theorem of Varadhan in 95, which is called the sector condition or strong sector condition. It's a condition about. I give you another one, and then I tell you how it is. Then there is a Set-Raman Varadhan. Now, Asians did quite well in this theorem, or Indians did quite well in this. Yao is not Indian, but you see, Varadhan, Set-Raman, Varadhan, Bhattacharya, so it's a good list. Good. That's 2000, I think. And in these papers, in various ways, it's about, the condition is the following, that in this paper the condition is, keep this Faradan, the condition is that phi be in the range of S1/2. S is L, because S is L. So mind, not in S, not in the range of S, this is bigger. Right? This is bigger. So this is a very important thing. And actually this is it is a necessary and sufficient. In the self-adjoint case, this is necessary and sufficient condition for the central. In these cases, you need something like S dominates A in some sense, which I'm not going to tell you because it's plus, so this is, I told you, it's always a condition about the operators and the condition about phi. In this case, the condition of the operators is this, and about phi is always the same. And phi, so let me call, this is the H-1 condition. This is what we call H-1. And this is always appearing, right? S dominates A in some very concrete sense, which I'm not going to tell you now because we don't use it, but that's the and of course, Varadan did all these things because he was interested in very concrete problems, not just to do an abstract theory. There were very concrete problems he wanted to understand.
So H-1, perhaps the name comes from
the name comes from the following. Why H-1? F phi in the range of S-1/2 is equivalent to saying that the phi, let me say the -1 norm of phi is what? With respect to this operator. With respect to this operator is the limit as lambda goes to 0 of phi lambda identity plus S inverse phi. But you can distribute this one, is a positive operator, half here, half there. So this is norm lambda plus S -1/2 phi norm squared, the limit as lambda goes to 0. Be finite. So that's why I say this is H-. This is an H-1 condition. Good? Now, and here is a theorem which I proved with two students in 2012, and I think I made propaganda for it because I think it's a very nice one. Relaxed, we call it relaxed sector condition. It's published in a special issue of this Taiwan journal which was dedicated to Varadan's probably 70th birthday, 2012, with students, so Ilves Horváth, Bálint and myself. And the theorem, let me not make it very broad, so the mathematics I will be a bit sloppy because time is limited, but I tell you the essential. Define lambda plus S, you have seen lambda plus S -1/2. By the way, this is defined in terms of the spectral theory again, because spectral theorem again, because this is self-adjoint operator. So this is a positive definite operator, positive self-adjoint operator. By the spectral theorem, this one which you see inside, this altogether makes sense by the spectral theorem. It's a bounded operator. And you have A, you have lambda I plus S -1/2. Call this one D lambda. And define between quotes, because this makes perfectly good sense. All bounded. This is bounded, this is bounded, this is bounded. Now, what I'm doing next, I put between quotes, because it's not that clear that it makes sense. S to the minus 1/2 A, S to the minus 1/2, and call this one B, but it may not. Now this is a tricky one because this guy is unbounded. It makes sense as an unbounded operator by the sector theorem, but two of them together don't make in between don't make sense, may not make sense. So this is a tricky thing. What happens, and what you expect that as lambda goes to 0, in some sense these operators converge to this operator. That's the question. Now the point is the following: in concrete applications, and in this case, in all this is not a okay. In all cases, which I know about, you can define densely this operator. You can find a dense subspace of the Hilbert space on which this operator is defined. So this is usually, I say usually because I don't have something that always, in concrete cases, it densely defined and skew symmetric. That means it's defined on a dense subspace, and on that subspace on which it is defined, it's skew symmetric. Right? This is usually. Now, my theorem is the following: if I can prove, and as I tell you, this is a precise mathematical theorem, but putting it in concrete, in very precise mathematical terms here would not.
Here you are saying A is skew symmetric?
A is skew self-adjoint.
Oh, I see.
A is skew self-adjoint. So L is minus S plus A.
Yeah.
S equals S star is positive, and A equals minus A star. And assume that they are bounded. It's more generally true, but let me keep them bounded, as in the case we are speaking about, right? And now the theorem is like this, and it's vaguely formulated, but it's a theorem, it's a proof theorem. Just I don't want to waste much time to. If you were able to prove about this operator, that it's not only densely defined and skew symmetric, but it's skew self-adjoint, so that its closure is the adjoint of it, or the negative adjoint. If B is essentially skew self-adjoint, and phi is in range, is in H minus 1. The range of S is the H minus 1. Right? Then the martingale approximation holds. So my condition on the operators is that this object, which is only formally defined here, makes sense as a skew self-adjoint unbounded operator. And the condition on the function is always the same, that it being H minus 1. H minus 1 is the range of S to the 1/2. And then the martingale approximation works. Right? Now this is a very abstract theorem. First of all previous theorems which are listed here follow. So Varadhan's, this was the strongest before, and follow. So assume any of the, this is the, so the point is that this is stronger, so this theorem is stronger than this one, this is stronger than that one, mine is somehow way because it's a bit different type, right? But this is stronger than that one. So the conditions of this one assumed that this follows, right? Okay, that's beautiful, but is it good of anything? And I claim it is.
So you use this to get to the L, right?
Yeah. To?
use this to get to the L.
Not to get to the L, but to get to the martingale approximation. L is there.
No, I'm saying that if it is true, then s to the power minus half times s and to the power s to the power minus on both sides, then that would be nicely defined.
Yes. Ah, you mean that that S to the, because
Yeah.
that's an identity plus,
So it would be nice to-
That's exactly what that does. Exactly what. Okay, that's what I mean. That I have identity. Okay, then you run away ahead a little bit. That what I will have indeed, what you say. Okay, what you say is that then if this is true, then I have S to the minus 1 L S to the minus 1 half. Yes, this is actually identity plus B. What? Then it's here minus, it doesn't matter. But what matters is that this is identity B is Q self-adjoint, so its spectrum is on the imaginary axis, so this is invertible. And that will matter, that this operator is invertible. You are right. And now let's go back to, so this was a digression to abstract theory. Now let's go back to my point. So let's recall, L was Laplacian plus sum over E in A M A times nabla A. But this is the same by the commutation. My commutation, this is minus sum over E in A nabla minus E ME, right? And this is the way I will write it first, right? Now take, so this is S, this is minus S, this is A. So my B is Laplacian to the minus 1/2 times nabla E ME times Laplacian to the minus 1. Good? Another way of writing it is from there. These two are equal. These are bounded operators, and I applied some commutation relations. Let me write another point. I put a prime there because I will see is Laplacian to the minus 1/2 ME nabla E. Oh, sorry, the sum is the same. Always the sum is the same. Laplacian to the minus 1. And you would be tempted to say that these two are the same, because these two are the same, and I just put them in, sandwich them between two Laplacian to the minus 1/2. But who mind that this is a formal thing I wrote, because these are unbounded operators. These are unbounded operators. But if I go to this form, I see the following. This is bounded, and as I told you, this is bounded. This is gamma E. This is bounded. This is unbounded. So the operator you see here is defined on the dense domain of Laplacian to the minus 1/2. That's the H minus 1 space. So this is densely defined on H minus 1. This is not the same operator. These are the same, but when you do this just juggling with formulas, then you have to be very, very careful when the operators are unbounded. Because here you have, this is a bounded operator altogether. This is bounded, but at the very beginning, say, you have an unbounded. So the range in which the domain on which it's defined is those functions from the Hilbert space from which, if you first apply this, then apply this, you land in H minus 1. This is a bit implicit. Now there are easy things you can prove about these two, namely that This operator is a priori bounded operator. This is a bounded extension of this one. This is defined on a larger tensor space than this one. Actually, this operator is the closure of that operator, but not the same. And the point is to prove that the adjoint is that. Or minus, negative that. Now, these are usually not easy things. This is what quantum mechanics is about. A big part of the problems that formally you define operators, and you have to prove that they are self-adjoint. So proving that this operator is essentially skew self-adjoint, that means on the domain on which I define it, if I close it, is the adjoint. That's difficult. I'm not going to show you because it's difficult, and it's very concrete computation. It boils down in the end to an argument of the following flavor. Not this argument, but an argument of the following flavor. Homework for the students, actually, what I'm saying now. Prove, okay, that's not even homework for the students, it's easy. That harmonic functions on RT are either bounded or increase linearly. There's nothing in between. There is no harmonic function which increases like square root of distance, right? It's not that this boils down to this statement, that boils down to something of this flavor. Proving, indeed, that this is big. In the end, this is a skew self-adjoint operator. And this is the main technical point in our work with Gaddy. In our paper with Gaddy, the first paper, the main technical point is, so we took all the ingredients from that previous paper of mine, and we knew what to do with the random walk and so on. The main technical result there was proving the skew self-adjointness of this operator. Good. Once we have this, then we have the martingale approximation. Once we have the martingale approximation, then it stays the same. Good. So that's about theorem 1. How do we stand with time?
You have 20 more minutes.
Sorry?
20 more minutes.
20 more minutes. Good. Now let me go to theorem 2. So from this all together, this first central limit theorem, the weaker one, follows. And let me now go to the quenched. The quenched CLT. There are 4 steps, actually 3. One of the 4 is just standard application of the martingale central limit theorem. So step 1. Step 1 is the following. For almost all omega in omega, it is true that expectation with fixed environment of, okay, maybe I made a mistake. There exists a finite constant such that of xt is less than or equal to this constant times square root of t. So this proves, this statement I will tell you how it comes up, and this is a difficult one. And this is tightness. It proves a priori, without knowing much, a priori it proves tightness of xt by square root of t, almost sure, so quenched tightness. For almost all omegas, the process xt by square root of t, so it's uniformly quenched. This c doesn't depend on omega. Good? And probably I should do it in maybe better I do it a slightly different way, because I'm not a bit confused now. Let me divide by t by square root of t, and let me take leaves soup as t goes to infinity, and this is separate. So that's the thing. Now, how does it come about? So this is extension. Okay, remind from yesterday that I have this condition. So the extra, here I need the extra condition that expected value or integral on omega. Remember, this H was the Helmholtz, from the Helmholtz theorem. Then the H minus 1 condition was that this is square integrable. And I said that I need slightly more. 2 pluses. B, Y, this is where I use this slightly more integrability, and for good reason, so there is good. Okay, now what you see here is indeed extension of a very, very one. There is a paper of John Nash back in 1958. Which is a famous one. It has thousands of citations. He didn't write many papers on analysis because he turned to game theory later, well, not much later, and his rest of the life did. But he did ingenious things in analysis before turning to the game theory. And this is about okay, he doesn't speak about probability, but actually, of course, he knew it's about diffusion, about elliptic equations, about estimates on elliptic equations, right? And essentially what he does, no, I should add something. He does, okay, more than that. Plus Osada, 1983 probably. And probably there are some other names to be mentioned here, which I don't know. Okay, there is Richard Bass has a very important paper. So there are many papers to quote, right? But what I want to say, so if you put together what was done before what I did here, was the following. Take, not on the lattice, but in continuum. Take the following diffusion generator, take L, be a diffusion generator, which is in divergence form, so where A is AX, A is AIJX, H is HIJX, A is symmetric, H is skew symmetric, right? And you understand probably what I wrote here. So you should say that sum over ij. You understand what's written, right? Now, and this is exactly, so if you think about this, that will indeed add a divergence. So this is the self-adjoint part of the diffusion generator, and this adds a divergence-free drift. This is exactly the divergence. So what you see, what comes from this part will be a divergence-free drift due to this skew symmetry, right? Now what Nash and Osada prove, Nash did only this part, that part. Osada realized what I mean that. Maybe others too, I don't exactly know the whole history, but simply these two names. If A is a matrix, right, is bounded from below and above, let's say A star times identity, this is a number, A upper star times identity. So it's elliptic and bounded, right? And H is bounded from above. H, say, like that. This is like a matrix bounded. And this is bounded term-wise, say. Right? Then take the diffusion. Let xt, this is not my xt now, xt be the diffusion with this generator, right? And what Nash proves without the term H1 and what Osada proves with the term H is exactly that sort of thing. So then this holds. It's a wonderful thing. It's a very, very beautiful paper. Of course, it's difficult to read because in 1958 people wrote in different style, but once you, it's a mathematical thing. Now, what did I do? What is new one? Because it looks like, okay, it's there. Putting it on the lattice, so the novelty, minor novelty, is that in on the lattice, so on ZD rather than RD. This is not a big deal, but there is something there, so it's not just drops out, but you understand what you should do, then you can. There is one minor nice argument there, which is really not there in the continuum, which I don't tell you, it's not a big deal. What is a bigger deal, major, and I could extend it, okay, mind, before I say, there is nothing like randomness here. These are deterministic coefficients. And the point what Nash was doing, he was interested in regularity of diffusions without, or bounds and so on, without assuming regularity of this function. So these bounds were valid uniformly, no matter how wide this A is. Before, there were only results assuming smooth A or Lipschitz continuous A and so on. And this could be just measurable. The only thing is the bound, and not bound on derivatives or whatever. So that's a big deal. Now, by major, what I call a major novelty here, that rather than assuming this H bounded, okay, my H is random, stationary, but I don't have to have it bounded, this is enough. So rather than, so H is in L2 plus epsilon minus, say, let me say this. So I don't, so, and that needs argument. That's really simple. So that's a new point. I don't have time to go in, so this would take me another 2 hours just to prove of this. This is the first part of the proof, first component of the proof. The second.
So, in the quenched case, you are able to get a decomposition like this of your L.
Yes, it gives, so my A is constant. No, actually, it's not just for this lecture my A is constant, because I assume, but my A, mind that the generator was Laplacian plus M, what I called M sum over E, ME. Okay, let me put it as if it was a diffusion, because then you can more easily compare it. So my dxt was dbt plus vxt dt, where v is a divergence-free random stationary field. So it's, if you write on the infinitesimal generator, then you get here Laplacian, A is identity, and H is the Helmholtz, H is the vector potential. In that's going in 3 dimensions. A skew-symmetric matrix in 3 dimensions is a vector. Right? So that's a vector potential. So that's exactly the same. But what's important, I want to emphasize that I don't assume it being bounded. If I assume it being bounded, that was there in Osada's paper. The bounded case was not. Osada did diffusion, so there is diffusion and lattice are not quite the same, but Osada did.
So this divergence-free condition gives you this skew-symmetric part
in
a suitable sense.
Yeah. Good. And now let's go to the second part. So I have, from here I have the tightness, I have the quench tightness, which is an important part, which I didn't need in the annealed result. Second, so-called harmonic coordinates. this is always what you do when you want to prove some quenched result for quenched central limit theorem or quenched whatever limit theorem for random walking random environment, and it goes back to Kozlov, it goes back to Osada and Kozlov. Osada didn't call it this, but he used in the 80s. And it has been used many, many times since then, but mostly in self-adjoint cases, or essentially only in self-adjoint cases, that is random walk among random conductances, which is the following. In my case, I put it in my case, but there will be novelty here. I will tell you what the novelty is. Give me a second. Yes. Okay, there was H. Remember what H was, the Hilbert space. I introduce another Hilbert space. Now, the space of gradients. So I introduce G will be the space of G, E, E, and E. So this in 2 dimensions, it has 4 components, right? All G of E are in H, and they are G of E omega plus G of minus E tau E omega in 0. That just tells you that G is a flow, but I need that it's a gradient flow. That means that for any, this is not very good, but okay. Okay. So G of for any E and say E prime in E, take any 2 directions. So what I'm going to write down is the gradient condition, that if you go around the plaquette with a flow, they add up to 0. Right? So that I have GE omega plus GE prime tau E omega is equal to GE prime omega plus GE tau E prime omega. This is the gradient condition. Right?
So the loop around.
That's the loop. The loop around any plaquette. So if you add the flow around any plaquette, you get 0. That's the gradient condition. This is a decent Hilbert space. Just another Hilbert space based on question.
It's a Kirchhoff condition for
What?
the Kirchhoff law in electricity.
Kirchhoff. Yeah.
Kirchhoff.
Yeah.
Yeah,
It's gradient. It's gradient.
if it follows, then it's a.
Okay. So these are gradients. And now the point is the following. Now I needed it for so the proposition is the following. There exists a unique solution in GD, or the G, not GD, we are in D dimension. So a unique solution in G of the following equation. Sum over, this is E. I use 2 different notation here, E. In E of P sub E omega theta sub E omega equals sum over E of E times P sub E omega. Now certainly this is an equation for functions over, and theta is the unknown. I want to find an element of this space, a gradient, which solves this equation. I tell you in a moment why, because for now you look at it why this and why not something else. Why this? Because if I solve this equation, then, and mind that theta, which being a solution, is a gradient, then I construct ket capital theta of x and omega, this will be sorry, what did I do? Give me a second. This is on the top of it. This is a vectorial. Yes, that's what I have. Why I have here a d. Why I have here a d. I understand. I didn't understand why. Because these are on h to the d. These are. It's a bit confusing because I have it gradient, but the functions themselves are vector valued. Vector valued functions which satisfy the gradient, the cycle condition, the cycle sum condition, right? And mind that this is so this is in RD, because this is in RD, and this must be in RD, so this is in RD. Each of them is in RD, and they must be a gradient. They must satisfy the gradient. Now, if this is the case, then I construct this field over my lattice, random field, for which this is the gradient. If this is a gradient, then there is a field of stationary increments to which is a gradient. So, such that, how should I write it? Yes. So theta such that of that plus e omega minus theta x omega be equal to theta, lowercase theta, e of tau x omega. So this is just a formal way of saying, so if this is a gradient, then there is a unique function up to pinning it down at 0, to which it is the gradient, right? Now, I solve that, and this is again a very easy exercise. Once, indeed, if this gradient solves this equation, then the process I'm defining now, let's say y of t be x of t minus this capital theta at x of t. This is random, it has an omega there, but everything is random, is a martingale. X is not a martingale, but if I make a, and this is what they call correct. So this is the point. So this is the equation the gradient of theta has to solve so that this be a martingale. Now once we have a solution of this equation, and that's my statement here, I will come back here why. I have this martingale. Unfortunately it's not this one, this should be, but not this one, not this one. But for this one I have the martingale central limit theorem. Is a martingale, okay, sorry. Is a martingale for almost quenched, is a quenched martingale. That means that for almost all omega, because that's an equation which is solved for omega, in fixed omega, for almost all omega, this will be a martingale. That means that I have for it, I have the martingale central limit theorem. Okay, here there is the martingale central limit theorem relies on an ergodic argument, but I have the ergodic argument. Right? Now what's left, I will come back to that one because that's an important point. What's left? So let me say this was the second. This was the third. The martingale central limit theorem is the third, but that's for free. Martingale CLT for Y. That's the third point, but I don't do anything for that because I just open a book and look up what the conditions are. And the last one is very important. Mind that this theta is stationary increment. In ergodic theory they call it a co-cycle. It's a co-cycle. Zero mean co-cycle. Now, zero mean cocycles are interesting. So the fourth point is that for almost all, so for pi, almost all omega theta xt divided by square root of t converges in probability to zero. Why is that true? Just the music. A zero mean cocycle. A zero mean cocycle should increase sublinearly. A zero mean cocycle should increase sublinearly. In one dimension, this is just the ergodic theorem, and I come back to what we discussed with this gentleman. What's your name? Opratim, this afternoon. A zero mean cocycle is just sum of ergodic sums, and that increases sublinearly due to the ergodic theorem. In principle, you expect that a zero mean cocycle on ZD increases sublinearly. But this is not quite true, because ergodic theory in higher dimension is more subtle than ergodic theory in one dimension. You need the so-called unrestricted ergodic theorem for this, which we discussed today, which is a bit stronger than Birkhoff, or a bit different than Birkhoff. Stronger conditions are needed than in Birkhoff. Maybe I come back if you allow what is that. But anyway, a sort of softish but not quite the most standard ergodic theory argument will help you to prove this. Because indeed, if theta was small order of distance, and I have a priori bound of square root of t, that was my tightness argument, then this will be small order of 1, because this is order square root of t. Theta at a distance square root of t is small order square root of t divided by square root of t. It's not that simple as I say it now, but this is how it goes. But there is some ergodic theory there, and there is some finer probability. Right? And you need more than just Birkhoff's ergodic theorem. You need this unrestricted ergodic theorem in higher dimensions. That means that almost surely, for all possible sequences of boxes going to infinity, you have the ergodic averages converging to the potential. Almost surely, for all possible sequences of boxes. All possible sequences of boxes in more than one dimension are not the numerable. In one dimension they are numerable, but not in. So in higher dimension it's a bit more subtle. Now let me come back to here to finish with this one. This equation is an equation in Hilbert space. This equation is an equation in Hilbert space. And in order to solve this equation, I use it, so I massage it as I can, and I put it in the end in a form like, the equation is put in a form like e to plus b, mind, what was b? Applied to some, say, chi, so it's a bit transformed, and it's straightforward transformations massaging, equals some f. And as we realized before, so this b is the b from the previous paper, which is proved to be skew self-adjoint. So this operator is invertible, as we just have seen. So this equation will have a unique solution, and do backwards the massage it in, and you get the unique solution of this equation. And that's the end of the story. So there are lots of various things coming together, and I think I should stop now.
Right. Questions? Comments? Comments? Questions? We are letting you go.
Super diffuse, but you haven't told anything.
I didn't say anything about the super
Exactly.
diffuse.
So we were just.
If you are willing to stay another hour, I'm happy to tell you about the super diffuse. I didn't tell you. So when you don't have the h minus 1, you expect super diffuse, and it's a different. That's a different story. That's a totally different story.
So I'm just trying to understand just one thing. about the super diffusion. You have the environment, yeah, and you have the original diffusion, right? Diffusion in the environment,
Yes.
or the process in the environment. Then is it some kind of correlation between the two in the positive correlation happening there?
I'm
That's
not sure I
right.
understand what
So I'm saying that suppose the environment and things are, so you see that variance increasing in everything.
Yeah.
Increasing because there is inherent variance in the environment and inherent variance in the process. So are they adding it up, or that's the super diffusive is going ahead, right? For example, suppose, just simple example, suppose you go along the path, one directional path, that would be order n.
Yes.
Because there is no probability, with the probability 1, you would be going as fast as n.
Yes.
Right? So you would be going at random at order root n, because you would be going like
Yes.
plus up minus up. So you are putting another random environment, right? So which is going those paths, but you are jumping from one path to another.
Yes.
So can you see it in terms of super diffusivity in the positive correlations between the two randomness?
I'm not sure. No, I don't know. I don't know the answer to this one. I don't know the answer. So actually, I can tell you, if you give me 5 more minutes, I tell you an example of super, just to have a super diffusive example. But I need
Yeah.
to
No,
to
sure.
give me some.
Sure.
Okay, so if I don't, okay, how should I put this? So don't feel like being obliged to say.
Sorry.
No, I give an example, and because that might be somehow related to your question.
Yeah. You gave me one example yesterday.
Yeah, but now I give you another.
Okay.
Because in that example yesterday, I didn't explain why. I just said that, oh look, that's super
Yeah.
Let me give you an example of a super diffusive and a diffusion example, so a continuous space, because it's easy. So let say V, no, this will not be, because we confused notation. Let phi be the two-dimensional Gaussian free field. Which is not a field. This is a discrete random distribution. But I make it smooth in a moment. Convolve it with u. So let u be u of x be just a function e to the minus x squared, just to keep things simple. But instead of that, you could have any approximate identity. The role it will be that, and let's take now the field psi be u convolved with phi. So this is on the large scale, it's not like the Gaussian free field, but locally it's regularized. Just locally, there's nothing else but the Gaussian free field regularized locally, right? If we are in 2 dimensions. And now I define V be the curl of psi. That means that V1 is d by d psi by dy, and V2 is minus d psi by dx. Good? Which makes sense because this is regular. So this is actually the curl, essentially the curl of Gaussian free field. Just regular. And now I define a diffusion at dxt be dvt plus this v. Now let's try to understand, because it's related to your question. This vector field is tangent to the level lines of that field. Take the level line, if we are in 2 dimensions, we have a scalar over a 2-dimensional plane, and this vector field is just tangent to the level lines. If I don't have this B here, then this motion will just run, will stay on a level line and run. But mind that the level lines of Gaussian free field are huge. So are not very confined. It could be really are closed. All level lines are closed, but but might may be very large, right? This BB gives some randomly, so that's what you said, that rather than going on one trajectory, you can randomly jump from the trajectory. Right? Now, what we prove for this one in a paper with Benedict Malko and myself back in 2012, we prove. Do you want to guess or? Okay. So what I said yesterday many times is larger than log t, than t times log t, and less than t times log t, and we expect actually to be but this is proved up here, and what I write here is the conjecture is of the order t times square root of log t. So we have no, I don't tell you how we prove it, but it's this sort of effect. If I understood you well, what you are saying.
Some sort of, can you, yeah.
Then you have some hugely fluctuating loops, but you jump between them, and that makes the diffusion strong.
So maybe you have both the kinds that you are saying, like you have a deterministic path and then there is a diffusive path. So both of
Yeah, that's it. Yeah. If you had only the deterministic part, you would be stuck to one level line, which is close. So you are, but the whatever small, I can put here any small stuff.
You have to just have a non-linear.
Just have something which
Yeah.
which pushes your way doesn't of one. And the discrete examples are very okay. This is what we could prove it for this one. We are struggling with the lattice modulus.
No more questions? Let's thank Bálint. Very grateful to you to come here.
I'm very grateful to all of you here and in Delhi and in Bangalore for all this hospitality. I enjoyed a lot. I'm tired, I have to admit. After 2 weeks.
We made you tired.
I give eight different lectures.
Yeah.
Which is, I'm tired, I have to say, but I enjoyed it a lot, and it was a great fun.
So the fifth one.
So thank you very much. Thank you very much for the invitation and for the hospitality and for what I got.